Hello, and welcome to the next part of this mini-mapper series. So last time we talked about some KiCad project setup. This time we're going to begin with schematic capture for the motor prototype board I'm making. And I'm not going to do the kind of live schematic capture or layout videos that some other people do, because there's probably no great benefit in watching me flail around in KiCad. There are other people who do that far better. What I'm going to do is I'll do the schematic capture and layout offline, and then we'll talk through some of the interesting features of it, unless I come up with some particularly clever trick that I want to show off, which is unlikely. So one thing I've started doing now is for each episode of this, I'll put a tag on the GitHub repository for the project so that you can see the state of the project as the video is made. I don't know if that would be useful for people. It might be quite useful for me. So let's get started by going and looking at the application note for this Toshiba motor driver that we're gonna use. And so this thing, like most of these things, it has an application circuit in it, and gives you a pretty good idea of what you need to do. So there's some bypass capacitors for the power. There's a bypass capacitor for this reference voltage. There's a sense resistor that we're going to have to deal with. We need to do something about setting this reference voltage, so we'll talk about all of that. And then the input and output connections are pretty straightforward. So let's talk about the power supply stuff first. The application note has some recommendations for bypass capacitors for the power and for this reference voltage. So that's pretty simple. Let's go and open up the schematic that I've made for this. Like I said, I've laid this out already, and so here you can see the motor driver chip. The motor, I've represented the motor as a motor in the schematic. The footprint that I'll use for this will probably be the kind of connector that we're going to connect. And similarly, I've just used a generic connector here for the inputs. You can see the bypass capacitors, 100 microfarad and 0.1 microfarad, which is what's recommended in the application note. There's a bypass capacitor for this reference voltage input here, 0.1 microfarads. So these are the things the main things in the application note. We need to deal with the sense resistor, setting this reference voltage, and then this stuff over here, which is something a bit different. So let's deal with the sense resistor first. If we go back to the application note, there's a bit about this current detection resistor, they call it, and they recommend values like this. And the way that we're going to calculate this is pretty simple. So we know, for instance, that the maximum current that we want to support, which is determined by the requirements of the motor, is 250 milliamps. We then need to decide what voltage we want to drop across the current sensing resistor. And the supply voltage for the motors is 4.5 volts. So we don't want to drop too much. And I decided that I was going to make the maximum sense voltage be 0.1 volts. So that means that when the motor is drawing 250 milliamps, you should see a voltage of 0.1 volts across the sense resistor. And so our sense is just 0.1 divided by 0.25. 0.1 volts, 0.25 amps, which gives you a sense resistor value of 0.4 ohms, which is in the range that they recommend. And so we can see this on the schematic, which I've temporarily lost. There it is. So I've just replicated this description here, said what the current is going to be and what the limits on the sense voltage are, and that gives you 0.4 ohms or 400 milliohms for the sense resistor. And you can calculate the maximum power dissipation in that when the current through this thing is 250 milliamps, then the power dissipation is only 25 milliwatts. So that's little, and it's not a bother. So we're happy with that one. The next thing to think about is setting this reference voltage that's used to determine, well, for the motor driver to actually control the current limitation mechanism that it has. And there's a little formula to calculate this in this application note. And we can fill in some of the things here. We know that I out max is 0.25. That's our 250 millivolts maximum current. Vref gain is given here. It's 0.1. We know the sense resistor value. We just calculated it. It's 0.4 ohms. And so we can calculate what the reference voltage that we need is. And it's 0.25 times 10 from this times 0.4, which gives you 1 volt. So that's the reference voltage that we want to put in on the Vref pin of the motor driver. And if we go back to the schematic and we look over here, we've got this formula from the application note here. We say we want 250 milliamps of maximum current. We know what the sense resistor value is, and we've got 1 volt. We know that the supply voltage for the motor is 4.5 volts. So 1 volt as a fraction of 4.5 is the same as 2 as a fraction of 9, which is 2 over 2 plus 7, which gives you these values for the potential divider setting Vref. So those are all of the things that are needed according to the application note. Well, one additional thing I wanted to do is to have a current sensing possibility. And so that's what this other part of the circuit on the schematic is for here. And we'll talk through that now. So the first thing we need to do here is to select an op-amp for this. So this circuit is a very simple low-side current sensing. There are lots of more sophisticated approaches that do the current sensing up here on the high side of the driver, but of the motor. But since the motor driver has a current sensing resistor on the low side anyway, we're going to do the sensing on the low side here. So this is an op-amp configured as a non-inverting amplifier, and it outputs a sense voltage on a connector. And one thing I may do when it comes to laying out the board is to bring all of these connectors together: the input, the motor driver output, the power connectors, and this sense voltage. I'll decide about that when I come to doing layout. So first thing to do is to choose an op-amp, and to do this, I like the TI part, and I very much like TI's documentation. So I just went to the TI website and had a look under their general purpose op-amps, and they have quite a nice little thing where you can search by circuit function. So they have, it's a bit small maybe. Can I make this bigger? Let me see if I can make this bigger. Yeah, but it doesn't really make the pictures much bigger, does it? Okay, so they've got an inverting amplifier, a non-inverting amplifier, a low-side sensing amplifier, and they've got a transimpedance amplifier as well. So if we choose low-side sensing amplifier, this is the circuit that we're going to have. We have our load, which is basically the motor and the driver, the shunt sensing resistor, which we calculated, the op-amp, and a feedback network. So what I did is I basically just went here, said one channel, power supply, 4.5 volts, input, so this is the maximum voltage across the shunt resistor, which is 0.1 volts. I said the input frequency would be about 100 kilohertz. We're not going to be sensing this very at any kind of high frequency, and this is used to set the gain bandwidth product limits for the amplifiers that they choose. And then the maximum output voltage, I figured that a gain of 30 would be good here. So that would mean that an input of 0.1 volts would give you an output of 3 volts, which is in the right kind of range to put into the ADC input of the microcontroller. So I said 3 volts here, and that's a gain of 30. Didn't select any fancy stuff, and you see there are 33 parts, and I basically went with the first one here, this TLV 9051. And there's one consideration for these low side current sensing applications is that you do need rail-to-rail operation. When the current is small, then the input to the op-amp is going to be close to 0 volts, and so you want something that has the term that they use is this input common mode headroom to negative supply, and you want that basically to be negative. And this selection process definitely gives you one that works for that. So that's the op-amp I'm using, and so here you go, TLV 9051. Then we need to work out the resistor values for this feedback network for the gain. And so I said I wanted an op-amp gain of 30. That gives an input to the ADC on the microcontroller of ranging from 0 to 3 volts. In this positive feedback setup, the gain is 1 plus RF over RG, and that means that RF over RG must be 29. So you need to make a voltage divider that has a ratio of 29. And you can sit down and try and fiddle with this all day, but instead what you can do is go to an extremely handy website. There are a few of these kind of calculators out there, and you can, oh, that was a bit funny, wasn't it? You can pick a resistor series that you want to use, so we'll stick with E12. That turns out to be good enough for the purposes here. You scroll down, you look at this resistor ratio thing, and this will find you the best combination of resistors to satisfy the ratio that you want, using values just from the series that you pick above. So we'll say 29, calculate, and this is just using resistors from the E12 series. So using 2 resistors, you can get within 4.5%. Allowing yourself to use 3 resistors, so either one on one side of the divider and a series pair on the other, or one on one side and a parallel pair on the other. Using a series pair, you can get to within 0.04%, but using a parallel pair, you can get an exact solution. So you have 330K on one side and 12K in parallel with 220K on the other side, and that's what it did. So we have 330K on one side, just here, and 12K in parallel with 220K on the other side. And that gives you a ratio between here and here of exactly 29. And that gives you a gain, going around this loop, of 30. And so your 0 to 0.1 volts here is transformed to 0 to 3 volts here. And that's basically it so far for schematic capture with this. There's some connections for the power stuff down here, but there's not very much to that. So what I'm going to do next time is I've started producing some mechanical drawings for the robot chassis and motor mounting and things like that. And I'm going to use those to look at the mechanical design of the motor encoders, because this is a slightly tricky thing where you have quite a close mechanical relationship between the motor encoder disk, we're using a disk with a photo interrupter, and the gap in the photo interrupter that the disk has to run through. And because the photo interrupter is going to be mounted on the PCB that sits on top of the chassis, all of these things have to be lined up pretty carefully, which means making some CAD models. So that's what I'm going to do next time. And then we'll be back to electronics. So I'll see you then.